Today we're going to look at complex numbers, and we're going to add, subtract, multiply, and divide complex numbers. First, let's take a look at what a complex number is. A complex number is a combination of a real number and an imaginary number. In this example here, I have 3 plus 6i, and 3 is a real piece, and 6i is an imaginary piece. When you think about number sets, the smallest number set that we have is the natural numbers. So, and then which is basically just your counting numbers, 1, 2, 3, 4, and so on. And then 1, 2, 3, 4. Then you have the whole numbers, they're a little bit bigger. You just have the natural numbers and 0. Then you have the integers, which is represented with a z. I know, it's a little weird. And that's your positive and negatives and 0. And then you have this one right here. This is the rational numbers. It's represented with a q. It's represented with a q because we can write a rational number as a quotient of two things. So that's all of your integers, but also all of your fractions or anything with a repeating or terminating decimal. Then you have your I over here. That stands for they're using I in this picture to represent irrational numbers. I haven't actually seen it with the I usually. I usually just write irrational on it. And then all of this is encompassed inside the real numbers. Now the complex numbers actually surrounds all of this, and then there's a separate little category over here of imaginary numbers. So even though 4i doesn't have a real piece, it's considered a complex number because it's like 0 plus 4i. And then even though like 5 is a natural number, that's still considered a complex number because it's 5 plus 0i. So every number is considered a complex number. Now I've used it already, but I is represented by the square root of -1. So if we wanted to work with this, let's say we had the square root of -4, we would break this down, this radical down, into the square root of -1 and the square root of 4. Well, the square root of -1 is I, and then the square root of 4 is 2. So this will be 2i. Okay. We could do another example where we had like 2 plus the square root of -32. Well, I'm going to break down the square root of -32. But this time, 32 is not a perfect square. So I'm going to list out some perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. So that's the first 10 perfect squares. Yes, 4 goes into 32, but 16 goes in, and that's a larger number. So I want to use as large of a number as I can here. So we'll have square root of -1, square root of 16, and square root of 2. 16 goes in twice into 32. So then I'll have the square root of -1 is I, the square root of 16 is 4, and the square root of 2 is just the square root of 2. Now I have 2 plus, usually we write 4i root 2. I tend to write my I before the radical so it doesn't look like it's underneath the radical. Now 2 and 4i root 2 are not like terms, and not like radicals, so my answer is completely simplified at that point. So there's some cool things that happen with powers of I though. So we already said I was equal to the square root of -1. But if I square both sides, I would have I squared, and then I'd have the square root of -1 squared. Well, since I'm squaring something that's a square root, the square and the square root can cancel each other out. I'm left with I squared is -1. That's a key fact for today's lesson. So I squared is equal to -1 every single time. But there's actually even more that we can do with this. So let's start with that awesome fact of I squared is -1. If I multiply both sides by I get I to the first times I to the second. Well, I to the first times I to the second. Since they have the same base, I can add exponents, and it'll be I to the third. And then on this right-hand side, I have negative 1 times I. So I to the third is equal to negative I. Fun fact. I can even do this with other ones. If I want it, starting again with that I squared is equal to negative 1. If I wanted to find out what I to the fourth is, I could square both sides. When I square both sides, well, I've got a power to power, so I multiply those exponents, like I to the fourth. And then negative 1 squared is positive 1. You end up with, whoops, this pattern that emerges. That I is just I. That doesn't have anything special. I squared is negative 1. I to the third is negative I to the fourth is 1. And then the coolest thing happens if I keep on going. I to the fifth goes back to the same I. And I to the sixth is negative 1. And the pattern just keeps on going forever and ever and ever. It follows what I call the circle of I. That I squared, this is I cubed, this is I to the fourth. And then each time I multiply by I, it just goes around this circle. So then I to the fifth is I to the sixth is negative 1, I to the seventh is negative I to the eighth is back to 1. And it just keeps going around and around this circle. And it's a really cool, fascinating thing about powers of i's. But today's goal is to do more than just reduce powers of I. We also want to add, subtract, multiply, and divide. So let's start with some adding and subtracting. We're going to add our like terms. So we have 3 plus 2i plus 4i. My like terms here would be 2i and 4i. And so when I combine those, I'll have 3 plus 6i. Take a moment, pause the video, and try the second example on your own. On this second example, which hopefully you tried, we want to be very careful to make sure we distribute the negative. Okay? The parentheses away. We don't need those. So when I do that, I'm going to have minus 4 plus 5. I'm going to do the same thing, though, of combining my like terms. I've got a positive 2 and a negative 4. That'll be negative 2. And then the other one I have is a negative 3i and a positive 5i. And that's a positive 2i. There's my real and imaginary part, that complex number. We can also multiply. So when I multiply, I've got 3i times 4i squared. Well, that's going to be 12i cubed. But wait, there's more. So if I go back to this list that we had earlier, I cubed, that's the same as negative 1 right here. So when I go to the next step here, I'm going to have 12 times negative I. And that's the same as negative 12i. Now, depending on how you approach this problem, you might have done it a slightly different way. It's possible to have done this problem a different way. It's possible that we could have had 3i, and then up here where I have 4i squared, I could have changed that I squared to a negative 1. 3i times negative 4, which is the same as negative 12i. So you get the same answer. There's a little bit of flexibility of when you reduce. And if you like smaller powers of I, like just working with reducing I squareds and things like that, you want to look to try and reduce those at the beginning rather than wait too far. The next one I have to distribute because I have a single complex number multiplied by this lovely binomial. So I'm going to distribute. I'll get 6i times 5 is 30i. And then 6i times 2i will be 12i squared. But wait, there's more. I need to replace that I squared with negative 1, which ends up as 30i minus 12. But mathematicians like to do complex numbers in the same pattern every time. So we always start with the real piece and then the imaginary piece second. Okay? It's real and then imaginary. Calvin and then Hobbes. Real kid, imaginary tiger. One more like these, and this particular one is a little bit harder because I have a binomial times a binomial. So I'm going to want to FOIL here. I'm going to multiply first, 3 times 2, then outer minus 3i, and inner plus 2i, and then one more, minus I squared. Okay, I'll start by combining my like terms. Well, wait, complex numbers only have two pieces, and I have three. Well, that's because I squared can be replaced with a -1. So I'm going to have a minus a -1, and those two negatives become a plus. So that is 7 minus I. Next topic that we want to look at is, actually, for this one, for squaring, we just want to have 3 plus 5i multiplied by another 3 plus 5i. And I'm going to FOIL here. 9 plus 15i plus 15i plus 25i squared. 9 plus 30i minus 25, because we're going to change that I squared to a -1. And then that ends up as -16 plus 30i. One more operation that we can do on complex numbers, and that's dividing complex numbers. When we divide complex numbers, we want to multiply the numerator and the denominator by the conjugate of the denominator. When I say conjugate of the denominator, it's going to look very similar, but instead of having an addition sign, it's going to have a subtraction sign. So it has the same number pieces, but has the opposite sign in between them. This is going to create a real number on the denominator when we multiply. Then we need to FOIL both. In this particular problem, I've got a binomial on the top and the bottom. Then we're going to have 20 plus minus 5i plus 12i minus 3i squared. And then when I FOIL the denominator, I'm going to have 16 minus 4i plus 4i minus I squared. I'm going to use I squared is equal to -1 to leave the denominator as a real number. And we're also going to combine any like terms. So I've got 20 plus 7i. Now this I squared, -3i squared, is going to be a plus 3. And then on the bottom, I'm going to have these i's cancel out, plus 1. So you end up with 23 plus 7i all over 17. The last step is to factor out any whole numbers if possible, and there's no number that goes into 23, 7, and 17. So that one's done. One last thing that we want to do is how can we do all of these same things with our calculator? So take out your graphing calculator, and the first thing you're going to do is hit the mode button. And you'll go down and change it from real to a plus bi. What that'll do is it'll let you evaluate square root of negative numbers. Go ahead and try that. Hit the second quit, and hit the square root of -4, just like we did earlier in this program, and see if you get 2i. Cool. There's one other really cool thing is we can actually do our addition, subtraction, multiplication, and division in the calculator as well. So what we're going to do is do 6 plus 2i plus 7i minus 3. Now, when you go to type this in the calculator, you're going to type it exactly the way it looks, using all of the parentheses that are there. Now, you might be wondering, Mrs. Marhefke, where is the I button? It's actually hitting the blue second button and then the decimal point. That will give you the I. So try the remainder of these problems with typing them into the calculator. This concludes the lesson on complex numbers.